Hi everyone, so my name is Yankang and today I'll be presenting my science fair project for CASPA and it's called Venturi Tube Wing Aerodynamics. Let's get started. So a little bit about myself. My name is Yankang and my nickname is Eric. I'm a rising senior at Doherty Valley High School in San Ramon, California, and my passions are motorsports, which are basically cars and racing, which is also related to the topic that I chose for this science fair project, and engineering in general. And I'm also an electronic music enthusiast. And a little bit about my mentor. So his name is Dr. Peng Ge, and he's a staff scientist at California Nanosystems Institute, which is located at UCLA. And normally we hold weekly online meetings to discuss the progress of our study, and Doctor will provide me with some valuable feedbacks and suggestions on how I can improve them. And the whole team is just myself, basically. I don't have any other teammates, so this is pretty much a solo project. Okay, and we'll break this down to 6 parts. So first part being introduction. So I'll talk about why I chose the topic of aerodynamics and what the project is going to be and what my hypothesis is going to be. And the second part and the third part, I will explain together. It's the design and method. So I'll basically talk about how were the devices created and how was the experiment conducted. And the fourth part and fifth part will be together. There will be result and analysis. So I'll present some of the data collected during the experiment and analyze what went okay, what didn't go as expected. And spoiler alert, it did go a little kind of like, yeah, not as expected. And final part is being conclusion. Just I will talk about future improvements that I can make and the implications of the study. Let's start from the introduction. So before we begin, we should take a little bit of conceptual course into racing aerodynamics. So when we talk about aerodynamics, normally we think about aviation or automotive industries. Well, in this case, I'm going to focus on automotive industry and specifically motorsports and uh, automobile racing. And there's a very core concept of the study. It's called downforce. So what exactly is downforce? Well, downforce is the amount of force generated by the aero parts on the car to press the car firmly onto the ground. So why is it important? Well, if we have more downforce on the car, that means we have better handling around the corners and the stability is going to increase. So that means we can take on corners on higher speed. So generally, this will decrease the lap time. This will make the car faster around this certain track if the track has a lot of corners and twisties. And on the top, you see a picture of Hill Climb Monsters. It's from Hill Climb Monsters, a YouTube channel. And it's a Lancia Delta with a fully redesigned aero package, and it's actually an active rear wing. So, and down here you can see the F1 inside picture. So it's explaining how downforce generated on Formula cars. So when the air gets sucked in and it goes through the underbody, it gets accelerated and through diffuser, and it kind of goes away from the car. Through this process, the airflow underneath the car in the underbody is increasing speed and therefore creating a low pressure zone below the car, and using this pressure difference from above and below the car, you press the car firmly to the ground. And the principle behind this is the Bernoulli principle and Venturi shape. Yeah, Venturi's effect, if you will. Yeah, because all of these aero designs employ some sort of Venturi shape. So what I want to do is I want to design a rear wing for a car that I can produce a lot of downforce, basically, regardless of air drag. And to produce this downforce, I've concluded with this initial design that I doodled this on Autodesk Sketchbook, which is on my iPad. And I planned to do an oval cross-section initially, but later I switched to a circular one because modeling an oval cross-section is too difficult for my ability. And I also consider varying the cross-sectional area from big to small to big again to create the venturi shape that we want. So therefore, I can increase the airflow speed when the air goes through the tubes, and therefore creating a low pressure zone on the suction side of the wing. So this low pressure zone will interact with the normal pressure zone, which is on the pressure side, aka the top side of the wing, creating this pressure difference, therefore pushing the car down to the ground. Hopefully it will produce more downforce and suppress the lift. And let's move on to the design methods. So for CAD modeling, CAD modeling, I picked Fusion 360. And to be honest, before this summer, I pretty much had no experience in this software at all. And I taught myself by watching tutorials in a few days and came up with this model eventually. Actually, I modeled 4 subjects for different purposes, and I conducted 5 tests in total. So for test 1, I'll test, oh, by the way, I think I forgot to explain. The rear wing that I modeled in the CAD software eventually will get 3D printed out, and then it will be mounted onto a 1/10 scale RC car. So RC stands for radio control, by the way. So the RC car will be Lancia Delta Integrale, and the chassis will be XV01, and they're all made by Tamiya, the model maker, the hobby model maker. So I'll show some pictures later on, but the car generally looks like this, as you can see on the right. And it's a real car. It's the blueprints of the real car, by the way, the real Lancia Delta. So why do I need this? Well, to mount the wing, you're gonna have to mount it on the hatch. So they basically close to the back window, and it's sloped with respect to the ground, right? So I want to mount the wing vertically, perpendicular to the ground. I want to mount it normal to the ground. So I need a mounting angle. As you can see in this model, you can see my mounting posts actually have an angled design. So how did I determine this angle? Well, I searched up the blueprints of the Lancia Delta car in real life, and I printed it out. I used a protractor to measure the angle between the roof line and the hatch, assuming the roof is perfectly parallel to the ground. And the angle turned out to be approximately 30 degrees. And then I drew a diagram on the blank sheet of paper. Using some simple geometry, I figured out that the mounting angle of the mounting post should be 150 degrees. And after 3D printing, the final subjects looked like this. So I'll have 5 tests with 4 subjects, because one of the tests I'll mount no wings at all on the car. So basically, what this test do is I'll run the car through a wind tunnel, mounted with different testing subjects or no wings at all. And underneath the car, I'll put a weight scale to measure the perceived weight difference under different airflow speed, so that I can get an idea of how much downforce or lift force it's producing. And for the 5 test, first one, I'll have a test when there's no wings on the car at all. And the second test will be the car will have a control wing, which is just a regular wing, as you can see right here, with no tubes. And the test 3 will be subject 1, as you can see on the bottom left corner, with each hollow tube 35 millimeters from the center line. And test 4 will be the subject 1 close, which is identical to subject 1, except the tubes were inadvertently made inactivated by having them stuck, by closing them up. And test 5 will be run with subject 2, with each hollow tube 25 millimeters from the center line. As you can see, it's 10 millimeters closer for each tube. So I'm moving the tubes closer to the center to see if that actually makes a difference. And the car looks like this. It's a 1/10 scale, so it's about 40 centimeters-ish long. And you can search up the exact dimensions on Tamiya website, I'm pretty sure. And I'm not going to provide these details because they're kind of irrelevant. and it's a 1/10 scale. And the chassis is called Tamiya XB01, which is a rally chassis with a relatively flat underbody for the sake of convenience when we conduct the experiments. And the wind tunnel. So as I mentioned, I will put a weight scale in the wind tunnel to perceive the weight difference under different airspeed, right? But the problem is there are no wind tunnels nearby my house or my school. And this is the first problem. The second problem is even if there are wind tunnels, they're usually very expensive to use. I've heard that they can cost a few $1,000s to use just a few hours because they're very big, very meticulous, very complicated, convoluted like devices, and normal people don't get to use it. Like you have to know some professors and stuff to do so. So which I don't have. So I thought to myself, why not just make one wind tunnel on myself, like on my own? It's not like the car is so big that it needs an actual wind tunnel. Like it's a 1/10 scale, so I can make a small wind tunnel, right? So I started off by buying a garbage can from Amazon. They're called $30, pretty cheap. And when they arrived, I took off the lid and I forcefully removed the bottom part to make the hollow, like to make the cylinder hollow, completely hollow. And then what I did was I had like a blueprint in mind of how I'm gonna design it, and I did all of this by hand on myself, like it's all handwork. I basically took a brushless motor system, which is a motor and an ESC combo. And why do I need a motor? Well, I need to mount a RC hobby propeller onto that motor so that when I turn the motor, the propeller is going to spin to create the airflow that we want. And by changing the speed of the motor, we can change the speed of the airflow. So therefore, you get all the functions of a proper wind tunnel, at least the core functions of the wind tunnel. So to do that, I have like a wooden piece that I cut off from a big wooden piece, bigger wooden piece, obviously. And I used the marker to draw out all the positions that I want to make holes of. And I used nuts and bolts and screws to get that onto place. As you can see, I get the motor onto the place. And I used 2 L-shaped brackets and 8 screws and 8 nuts to mount the wooden bar with the motor and the ESC onto the garbage can. And for the garbage can's mounting position, I used a L bracket to measure out the distance, and I used a white marker to mark that on the garbage can, as you can see on the picture here at the bottom. And I used like a hand drill to drill the holes out. So it's a very tedious process. It took me a few days, like working nonstop to get this done. So after it's done, I'm actually pretty happy. And by the way, the ESC and the receiver, as you can see here, they're mounted with double-sided tape. This receiver is later switched to an Arduino Uno. These are just some pictures of working process, sanding the wood down, making it look good and stuff, and making it fit. And the mounting. So when I finish making the wind tunnel, I need to mount it somehow, right? So to do so, I'm making it sit horizontally to the ground. And to mount it firmly, I'm thinking about gluing it down to the cardboard piece, but merely just gluing it with normal glue without support is not enough because the motor is going to turn very fast at 3,000 RPM, actually like 8,000 RPM during testing. So it's going to create a lot of force and torque. Without like a very strong support, the thing's going to break off. So I ventured to find a stable way to mount it. And I eventually settled with 2 wooden bars, as you can see on the bottom left corner. And I kind of like did a test fitment, and I measure, I didn't measure, I mean, I did a test fitment with the 2 wooden bars and the wind tunnel. I marked their positions where they can stick tightly against the wind tunnel without letting it lift off from the ground. And I used a construction adhesive, a polyurethane, to glue these 2 wooden bars down, and then I applied some more glue onto the cardboard, like, area in between these two bars, and I stick the wind tunnel on. And I put something very heavy, a very heavy object inside the wind tunnel to press it down, and I let the whole thing sit for a day or two. It turned out to be very strong, very sturdy. Reason why I'm using construction adhesive is that I don't think normal adhesive will do to provide the rigidity that I want. But these are very dangerous, so I don't recommend trying that. It's very toxic, very dangerous, and extremely sticky. And then we can talk about Arduino. So the reason why I'm using Arduino Uno is I want to control the motor's angular speed, I want to control its RPM, and I want to visualize how much the motor, how fast the motor is turning. Even if like I'm not, even if I cannot directly see the RPM, I can still somehow using the COM5 serial monitor to have a serial number and a potentiometer to visualize how much percentage of the throttle I'm opening, and using that percentage of throttle, I can calculate how much voltage from the battery is actually going to the motor. And using that voltage on the motor and the kV value of the motor, which doesn't change, is 2,200 kV, I can get the exact RPM that I want. So if I reverse this entire calculating process, I can get, if I want to make it spin at exact 1000 RPM and my battery's at a certain voltage, I can calculate how much do I need to turn the potentiometer to make a certain value on the serial monitor. And here's the code. I kind of like researched on the code and I kind of borrowed this from others. Well, yeah, it's kind of shame to say, but I have no prior experience in C language at all. In school, I learned C#, and C is like something a little bit new to me. So I spent another few days kind of getting the basics concepts down. And yeah, that's the story. To regulate the speed of the wind, I just control the RPM of the motor, as I mentioned. And the battery I'm using is a 7.4 volts LiPo, which is lithium polymer 2S battery. It's 1,500 milliamps per hour, and milliamps hour, not per hour, sorry. But it doesn't matter. And here's the setup, as you can see on the right. And there's the board, there's the ESC, motor, potentiometer, all connected. I soldered these jumper wires onto the potentiometer. That's not too much of the hard work. It's just a little soldering job. And there's the calculations you can see. I've already explained this. I'm not going to explain it another time. And a final setup looks like this, which is I'll have the computer here to have the COM5 monitor on to visualize the throttle percentage of the potentiometer. Oh, I think, by the way, on this COM5 monitor, if you turn the potentiometer, you'll see a number popping up. And this number could be anything from 0 to 1023, depending on the twisting, like how much you're twisting the potentiometer. If it's not twisted at all, it's 0. If it's twisted fully, it's 1023. So you can map this 0 to 1023 range to the voltage range of the battery, which is from 0 to whatever voltage your battery is charged on. And in this case, the battery's 7.4 volts. So when it's fully charged, it's 8.4 volts. So in this case, it's from 0 to 8.4 volts, corresponding to 0 to 1023 on the COM5 monitor. Right, so that's how we did the calculation. So on this computer, I can just visualize that number, and through some calculations, I can get what exact RPM is the motor spinning at. Oh, yep, and now we can move on to data. Oh, I forgot to mention just now, like the weight scale is already put into the into the wind tunnel, and it's a scientific weight scale. And test 1, we have no wings at all. Test 2, we have control wing. Test 3, we have subject 1. Test 4, we have subject 1 closed. And test 5, we have subject 2. These are pretty tedious data, and I don't recommend I mean, it's not like I don't recommend, but it's just explaining the model will take too much time. So I'll leave this to judge review of the presentation PowerPoint itself. And bringing it all together, you can see the average lift force is actually increasing when you're installing a wing, which is going completely opposite from my hypothesis, because I hypothesized that it's gonna suppress the lift and create more downforce. The situations that it's actually reversed. So I'm gonna try to explain why it did not work. So we need a more thorough understanding of aerodynamics. It turned out that, first of all, the wings did create some force on the car. It's just not the downforce that we want, it's the lift force instead. Second, the airflow around the car may be more complex than we imagined because the wings mounted on hatch and there's air coming from the side of the car, there's air coming from the roof. So it's a much more complicated situation than I thought. And the airstreams flowing into the venturi tubes, into the tubes underneath the wing, they may not be parallel to the tubes. Like they may go from sides and all those directions. And the closed tubes are actually reducing some of the lift force. So that means the tubes are actually creating more low pressure zones on the top. And speaking of this low pressure zone, which leads to one of my hypotheses of why this did not work, like one of my theories, is basically that the tubes are creating so much low pressure zone on the top that the pressure on the top is actually, I mean, on the top of the car, underneath the wing, that pressure is actually getting lower than the underbody's pressure. So it actually kind of pushes the car up from bottom. So that's one of my theories on why it didn't work. And another theory would be that the center of pressure, as you can see on the right, because center of pressure is actually very important because when only the rear of the car experiences downforce, the car will rotate around the center of pressure, which will press down the back but lift up the front. So the pitch angle will become positive. So this lift force on the front may or may not, it may surpass the downforce that we created. And in that scenario, we're actually creating more lift than downforce. So pretty magical, right? So, and another thing I discovered from the data is that better downforce achieved when the tubes that I made are closer together. So when they're all at the top on the roof of the car. So that may be explained by my airflow theory, because when the air flows like on the top, like through the roof, it's probably just more uniform, it's more predictable. And when it goes through the tubes, it actually reduce some of the lift. Because this can be shown by comparing data from subject 2 versus subject 1. And another very obvious error of this experiment, human errors. First of all, the experiment was not conducted in a lab environment. It's all conducted in my garage. And although I tried my best to control the climate of the garage, I controlled the temperature, the humidity, and the barometric pressure by not opening the garage door for 3 days. But that's all pretty much. There's just so much that I can do because it's not a professional lab environment. And another thing is human error is like when I'm making the whole thing happen, when I'm making the wind tunnel, when I'm making all this stuff, it's all handwork, it's handcraft. So it's gotta have some sort of fitment issues and errors here and there. I cannot make them as precise as machined professional tools. So yeah, kind of frustrating, but at least I'm getting a better idea on aerodynamics and how or why this doesn't work. And the biggest takeaway from this study is that aerodynamics should not be just one part. It should not be just one part of the car. It should not be just a rear wing. It should be an entire package all around the car, acting together to produce the downforce that we want. So which leads us to the conclusion and our future implications of the study, like the future improvements that I can do. So my plan is to create the full aero package for the Lancia Delta RC car model by having a front splitter and 2 front dive planes, which are also called canards, and the side skirts to seal the air from the side to have like ensure a cleaner down underbody airflow. And rear tube wing, which is subject to, I'll continue using that because that seems to be the most effective throughout the testing phase. I mean, the testing that I've done. And I'm going to also design a rear diffuser on the back of the car. And on top of all of that, I'm going to make sure the underbody is completely flat and clean. And I'll change some of the screws from like crisscross to hex for easier maintenance and to reduce the drag on underbody just a little bit. I mean, yeah, anything matters, right? Even the tiniest detail. And another thing that I should pay more attention to, since I've been the hardware person throughout my entire life, I'm still getting familiar with all the computational tools. As you can already probably see, I've already explained that I'm not that familiar with CAD softwares yet, and I'm not that familiar with C programming. So I'm gonna work on those skills to get myself familiar with this powerful tool of internet and computer. And I'll also look into CFD analysis, which is computer fluid dynamics. So when I have the SDL model ready, I can input those models into the CFD software, such as Foam. Is it called OpenFOAM? Anyways, I'll put that into the software, and it can analyze the air, the pressure, the concentration area, the airflow, the downforce you're like producing. It can all simulate that. So it's a very powerful tool, and I should definitely look more into that, so that I can do more simulations before I actually put it on the car. And these are resources that I referred to. Yep, not too many. And that's it. Thank you for listening to my presentation. And if you have any follow-up questions, or if you are more interested in my project, my email is always open, and I check them on a regular basis. I have 2 emails that I check very often, which is Yankang 2018 and Keenum142857. And although you can also see my phone number in case you really want to call me, but yeah, I guess that doesn't really matter. But yeah, I'll just still put it on there. Yeah, that's all. Thank you, and goodbye.